Okay, hello everybody. Thank you for coming for this um, Cruise Lab, Cruise Data Science Initiative Lab. This is the Lab 6. So I'm going to start already sharing my screen and I'm going to start the conversation. Okay. So for the lab today, we are going to be talking about salt identification in seismic sessions using Tensorflow as a deep learning solution. So today we are not going to be using R. Today we're going to be using Python because we're going to show how to use TensorFlow and how to create a model for image segmentation. So for the agenda of today, we're going to talk a little bit about the Cruise Data Science Initiative as an introduction, an overview of what you're trying to do today. I'm going to talk about the image segmentation and why it's different than classifying images like classifying as a dog or as a cat. We are declassifying objects inside an image. And just an introduction to TensorFlow 2, where to download and everything like that. We're gonna work a little bit with the Google Collab and then some closing notes after we do the presentation of the codes. So the hosts of today, it's me, Marcelo Guarido. I'm a data scientist with a PhD in geophysics, and I'm head of the Cruise Data Science Initiative. And the co-host is Daniel Tread. Daniel, would like to present yourself?
I am associate professor here in the Department of Geoscience and associate director of Cruise. And we're collaborating with Marcelo in this data science initiative.
Yeah, thanks a lot, Daniel. I'm collaborating a lot. So let's start. I'm just going to demonstrate the code that you're going to be working with today. So I'm just going to share the screen. So you're going to be, ideally, we would be working with the Google Colab and with a Python notebook inside the Google Colab. However, it's taking too long to load the data into there. I'm going to explain how you're going to load the code to the Google Colab and how to mount your Google Drive or how to include your data inside here. But apparently it takes too long because we have a lot of images. We have in the total 8,000 PNG images. So it's taking a while to complete this step. So because of that, you're going to be actually working in a Jupyter lab just to show the codes. So going back to the presentation, the Cruise Data Science Initiative, we are a new initiative in Cruise where we are focusing on doing machine learning and data science projects, focusing on the geoscience road, but we also do other type of projects that could be involving engineering, HSC, and other stuff. And we are mainly focused on the academic research, and also we have some industry research. So we do both. We also provide some training, like for programming in R, Python, and MATLAB. That could be like some introductory training for programming, or could be something a little more advanced, like for applications in machine learning and AI, and even how to actually create apps. And we also are offering those learning labs. Those are these webinars that you have every 2 weeks. The one that you're having today is one. And you can access all the information from the previous labs in the Cruise website. So if you click in this link in here, you're going to the Cruise website.org, and you go to the research links on the top and data science on the sidebar. So we have the information about all the previous labs in here. Okay, so going back to the presentation, let's just do an overview today. It's a very fast overview. What you're going to be doing, you're going to be trying to identify salt bodies that we have in the subsurface of Earth inside some seismic images. It's quite important to identify the salt because they kind of are very difficult to image below and sometimes on the sides of a salt dome. depend of the shape of the salt dome. So this is an example of this salt dome and how that would be more or less be seen in the seismic image. So we are gonna try to identify this shape in here, okay? So first, let's talk about the image segmentation. It's very common that we see in Google or everything. If you want to see images of dog, cat, or car, you just search, and it's going to show you images of what you're looking for. So there are models that can look at this image and say, this is a cat. Okay, so you're going to have a model that's going to search of different options that it has, different classes, and by the trained weights, it's going to identify as a cat. It's done by doing a convolutional neural network, where we have some images, in this case, it's a car, where we are going to create some type of features, learning. We are going to extract some features from this car, like everything that is a border of this car, everything that's horizontal or things like that. We are going to convert these to probabilities, and they're going to see what's the probability to be each kind of those items. It's done with something called the convolutional neural network, where, for example, we have this car here, and we have 3 matrices. This means that we have the red, green, blue colors, so those are the color channels, and we start to apply some convolutional convolutional layers. We're going to convolve this image with a smaller window to create a new type of image, where this width here means the number of filters that we have. So usually the image is going to be a little smaller, the next one. So by doing these convolutions one by one, like we are doing here, you're going to end up with these learned features that this cubic form here is actually a bunch of small images with features learned from the original features, and then it's thrown to a fully connected layers in neural networks, where it's going to classify as car, truck, or anything that you have. However, this is not what we want to do in our image. What we want to do is we want to identify objectives inside our image. In this example, this is from the MATLAB website. It's identify everything that's car, bus, sidewalk, building, trees, and so on. So that's what you want to do. You want to take a seismic image, identify what is salt and what is no salt by classifying pixel by pixel of the image. And it's done by using something called IOU-Net. It's very similar to the convolutional neural network, where we have those convolutional layers, where we're starting to decrease the size of the image, but increase the number of features that you are extracting from the image. This is called the encoder side of the IOU-Net. And then when we have the compressed representation, those are all the small features that we're extracting from this image, we start to localize those features in the image. We are going to end up with several matrices of probabilities for each one of the objectives we have here. That when you convert to classes, you're going to have the image segmentation. In this case, it's classifying what is the pilot and what is the motorcycle in here. And everything that is not is in black. So that's what you're going to be using is the TGS salt identification website, a challenge dataset. So you can find this dataset in the Kaggle website. So I'm going to the Kaggle website just to show. So I have it open in here. If you go to the Kaggle website and search for the TGS salt identification challenge, they provided a bunch of PNG images that we have the seismic images and also the masks that mean what is salt and no salt. So it's a matrix of zeros and ones, 0 no salt and 1 salt. And we want to identify what are the, we want to create a model to identify the ones, to find the ones, that means salt. So you can come in here to this, the competition is over already, but you can do some late submissions. So you can come here to the data side and you can download everything. You can download the train, the test, and all the information that you have from this competition. In our case, we are just going to be using only the train.zip that comes with this. I'm going to show here in the folder. So when you have the train, that's the zip file. Inside, you're going to have the images and the masks. The images, those are the seismic images. They are just small batches of a seismic session. We're going to have 4,000 of these. And for each one of those images, we're going to have a mask that is just those matrix of 0 and 1 saying which pixel is not salt and which pixel is salt. So the white one here means salt and the black no salt in this plotting here. So that's where you're going to download the data if you want to follow. We are not going to provide the data tomorrow because it's too heavy. So it's better for you to come here and download. So going back to the presentation, you're going to be using the Tensorflow 2 to create our model. So Tensorflow 2, it's a library that is mainly used in Python, but you can have it for C++, for R, and for other languages. And it's a framework where you can create very powerful machine learning applications. And it's very common to use deep learning using TensorFlow. So if you wanted to install TensorFlow, you go to the TensorFlow website, where I'm gonna here. It's gonna show. So it's tensorflow.org. And you have all the information how to do the installation. So if you want to install, you come here to this tab. So you're just gonna say, what's my operational system? If you wanted to install, use GPU. In this case, we are using GPU. And if you needed to understand what is the GPU guide, you come here. So this is how you're going to install, just a pip install TensorFlow, but you need to install a lot of things related to your CUDA to run in your NVIDIA GPU. So it just works for NVIDIA. If you have the AMD GPU, probably it's not going to work for a GPU. The next one, you're going to be using the Google Collab. Google Collab is just a way to run your Jupyter notebooks or Python notebooks in the cloud, where you can upload your code and your data and run there. They are free to use, but with a little tweaks. If you're using the free account, you have just 12 hours to create a session. After that, the session is going to be closed. But even though it's free, you're going to have access to GPUs and TPUs. If you want to get a paid version, that's $10 per month. It's possible to create a session for 24 hours and you have more powerful GPU and more powerful TPUs. So you're going to just show how to use the Google Colab. So let's go for the demonstration and for the codes. Here I have it open already, my Google Colab. So, but I'm gonna show you how to open from the scratch. So I'm just gonna search in here, Google Colab. Okay, so when you come here to this Colab research.google.com, it's actually gonna open already a first notebook as example. So it's not exactly, you don't have like a home web page. When you enter to Google Colab, you're already in the coding session. So if you want to add, I'm just going to need to change my account here because this is my personal account and I have my university account where I have my stuff installed. So let me just close this one. It's a little hard. Oops. So I'm closing this one. So this one that I have my university account. If I want to upload one code, I can come here, do File, and Upload Notebook. So I can choose a file. I can choose a file from my disk. So I have in my Google Drive folder, I have the salt identification codes, and I'm going to upload my Python notebook. That's the salt underscore identification underscore TensorFlow 2. So when I open, so it's just going to upload the code, and now it's going to show in here. Another way that I can do, if I already have the code in my Google Drive, I can come to my Google Drive web page. So I go to this salt identification folder in the web, my codes, and okay, that is weird. Oh, okay, I have a bunch of images here that they shouldn't be here. Okay, so let's not do that. So another way to do, I'm gonna do an easier way. As I'm inside in here, in my Windows, inside my Google Drive folder, I can just do right click in here. Oh no, I can't, sorry. Forget about it. So let's just keep the way that we uploaded it in here. So after you upload, you want to get your data set in here. The easiest way, if you have your data set in your Google Drive, is to mount your Google Drive folder in here. So the easiest way is to run this chunk of code that is going to appear if you just press this button in here. When you run, Shift Enter, you're just going to be sent to this link that you click. You select the account that you want to use. Just allow. And you copy this code in here. Come back here and paste. What happened? Now you're going to mount your Google Drive in here. So it's just going to take a while. So I'm just going to do this and come back. Now I have my drive in here. So this is my Google Drive. That should be in this My Drive. And I have here my salt identification and have my codes and my train, everything. However, when you look to where you are here in the code, let's just do a Linux command where I use !ls or pwd in this case. If you run this, we know the location that you are. We are in the content that's not a folder that you actually have in your Google Drive. This is from the Google Collab. And if you do ls, so we are here. Actually, we are in this root folder, basically. So if you wanted to have access to our data, we need to change the directory that we are working here to the one that we have the codes. And that's how I did. I imported this library OS, and I just use os.change directory and the location that I have. That should be here. You enter here. You enter in the salt identification in the codes. So I have my codes inside here. A way to get this address, I can just close it here because I don't want to see the figures. I come here, just click on these three dots, and I can just copy path and paste inside here. So that's the easiest way to go to your location. So should be that. When you run in here, now if I do my ls, I'm in this folder where I have all those images. Okay, so I'm just gonna close this one. I'm going to the other code that it was already open. I'm just gonna leave this. I don't want to run anything in this. And this is the one that I opened before. And I think that I told you is that to upload the images that we have in that training folder is taking a while. So I started it 30 minutes before the meeting, and it's still loading. So that might be a problem to use this situation. Might have a easier or smarter way. Those are other ways that you can upload files. If you run this coding in here, when you click, you're going to select the data that you want to be uploaded in another window. And so because of that, we're going to use the JupyterLab to go. So this is the same code that I have in here in the Google Collab. It's showing here in my JupyterLab. So in the folder that is going to be provided to you, we are going to have the TensorFlow code. That's this IPython notebook. We're going to have this Keras model. So it's a modeling that we trained before, and we're going to be providing to you, because to train this live is going to take a while. We took like 8 hours to train this model. And the history, how was the history of the training of this model? And we are going to also be providing, besides the coding that we have here, we're going to be providing not the training data, but the location where you can download the data, because it's quite a, probably it's a heavy one. We're going to check if you're going to provide this or not. So I'm not going to run these two first cells, because those are for the Google Collab to mount. So here we are just import some libraries that you're going to be requiring and going to be using for plot and for training. So you have a lot of the TensorFlow. You're going to be using the Keras package inside of the TensorFlow, the Keras unit, and all the layers that you're going to be using to construct our model. So this CV2 is this library, OpenCV. This is going to be used to load our images from PNG to NumPy arrays. So that's how we're going to be doing. We are just going to set the location of our training images and our masks, and just getting the list of the images that we have on each one of them. So they actually have the same name from both images and masks, the name of the figures, so they can be matched when you load. They are just in different folders. And here is how we are going to be loading. So we are doing the cv2.inread, that's an image read, the folder, that's this one for the training, plus P, where P is each one of those images that we saved in here. So this is a list comparison method that we are using. And we are loading the images as grayscale. Instead of to have 3 channels of color, you're just going to have 1 channel that's go from 0 to 255. And that's one of the reasons that we are dividing by 255, because Keras just works better for images or for data that's gone from 0 to 1. So both for the images and for the masks, you're going to be divided by 255. So for the mask, because of that, you're going to have 0 and 1s, and here values between 0 and 1. So I already ran this part because it takes like a couple minutes to load. And what you are printing here is the shape of the train images, the seismic images, and the shape of our masks. So we have 4,000 images, each one being 101 by 101 pixels. To make our, so I'm going to jump those cells as well, because this is just to load from in our Google Collab. We're going to be creating here a function where you can resize the image. So to create our UNet that you're going to be creating, we are using images that has size in both sides as a power of 2. So the closest power of 2 of 101 is 128. So we're going to be resizing each one of those images by 128 to 128. So we're just going to run this cell. So it's going to be resizing the images. And this one is just to plot the seismic images and the salt overlap them. And this K means what is the number of the columns and number of rows you're going to have for this image. So it's gonna take random images from your 4,000 images that you have, and it's gonna be plotting the seismic one overlapped by the mask. So those are the training data that we have. So we have seismic, and in green, we have the salt, that should be the 0 and 1. First few things that we have to note from this training data set is that the training data set is not perfect already. So it was probably done by someone that was doing the interpretation of the salt and using some interpolation software to go in between. Because if you look, for example, in this image, I don't believe this area is salt, but it's marked as salt. The same occurs in here. I don't know what is this green being marked here. Probably some things caused by interpolation. The same in here. So we are not. This means that even our model being trained the best way possible is not going to get perfect, because it's also going to learn some mistakes. Okay. Another thing that you have to do for the TensorFlow Keras modeling is that we have to expand the dimensions to have another dimension for the images. Those are the channels. We just have one channel. It's a grayscale. We just have one color, but you can have up to four colors if you have red, green, blue, and alpha. Or you can use these channels as other attributes from the seismic as well. You can create attributes and use it then as channels, but we are not going into that. So the challenge provided also a testing data set where you got your score from, but we don't have access to the labels of the data set. So what you're going to be using just to test our modeling, we're going to be separating 20% of those images, means 800 images to be our test. So we're going to be separating both as X train and X valid, means those are the seismic, 80% for training and 20% for the validation, and for the masks as well, for Y train and Y validation. We're going to be using this function from the scikit-learn train test split. You're just going to be including our X and Y, and it's going to separate the same indexes for each one of them. So we are just testing size 20% and the random state, so they are going to always select the same. So it's a pseudo random selection. So here we are just selecting those. And one thing that was really helpful for us during the competition is to create new images based on the images that we have, to have more options for the model to train. It's quite hard to create other images from the seismic one. So what we are doing here, we just flipped those images for the training. So we flipped left and right and upside down. So we are going to have 4 times more figures than we have before. This is not as perfect as having new images, but that helps in the training. So just doing here the flipping now, just running, and here I just plotting some of them from different parts of the data. So this is the original one, this is flipped left right, this is the upside down of the original one, and this is the upside down of the flipped left right. So we're going to have 4 times more image. And in the end, for our training, we're going to have 12,800 images for training. Okay, so now we need to create our UNet model. So remember that you had that encoder area where we are just applying the convolutional layers, where we're going to be decreasing the size of the images and extracting the features, and then we are going to be locating those features inside the image. So, and that's how we create a simple UNet model. We have to select the first layer, our input layer. So, and it's gonna have the input size of the image. So we have 128 by 128 by 1. And in here, we are gonna start doing our first part, or could be the first layer of our UNet. So we are doing some convolutional, 2D convolutional. This 64 means that you are applying 64 filters that are square, 3 by 3. We are going to have an activation ReLU for our activation function. This padding same means that we are just keeping the image of the same size as the input. So we're going to keep 128 by 128, the size of the image. And this is just initializer of the weights. So you can select different ones. After that, you're going to do a batch normalization. You're just going to normalize the values of this convolved layer. And then you're going to apply a second round of convolutional layers as well, with the same as above. Another batch normalization. And then this max pooling 2D, it means that you're going to be decreasing the image in the size of a 2 by 2. So by each side is going to be divided by 2. So the image is going to be 25% of the original size. So we are reducing from 128 to 64. This means that for the next one, we can apply more filters. So all those encoder side in here, they have the same shape. If you look into here, we are just increasing the number of filters that you apply on each layer. And here, we are just using a dropout in this area, where we are just removing 50% of the weights randomly. So this is to avoid a little bit of overfitting. Here would be the center area that in our presentation, if you go back, now we have this area in here, the compressed representation. So that's the center area. And then now we're going to start to do the decoder, where we're going to start to get the image to the original size that we had before. We have to do some transpose 2D, where we're going to be converting to from 8 to 8 pixels to 16 to 16 pixels. Then we are concatenating, doing a merge with the output of this layer that you had in here. This is a way to localize your features inside of this part. And then you're also applying more filtering, more convolutional 2D, and batch normalization. And we're going to keep doing, increasing the size of our image and locating our features until we end up having a layer that's back to 128 in the images, with a final layer. We're just going to have one filter with one stride, means that it's going to be with an activation sigmoid. So it's going to be outputting a matrix of probabilities to be 1 in this case. So how this is a binary classification, we just need 1%. That's the percentage to be solved, or in this case, probabilities. And then we just created this model in here, and here we're going to be returning the model. If you already have some pre-trained weights, you can load it in here, but we don't have yet. This second modeling is just a very simple UNet that maybe if you don't have GPU, it still might be possible for you to run it. But as it's too simple, UNet, you're not going to have a great result from it. So if I run this, so I'm defining this function that I created the UNet. So I'm going to define my model to be the UNet, that's a more complex one that you created above. Apologize. And that we're going to have. We set our model to be that more complex UNet, and you can check the summary of our modeling. So this is a comment from the TensorFlow. So we have all the layers that we created, how many parameters we have on each one of the layers, and by the end here, how many parameters we have to train. So we have to train basically 31 million parameters in this one. That means that we need a large amount of data. So that justify why we're creating more images, why we did that image augmentation, data augmentation. Here, we are just going to be compiling the model. So after you create the model, we have to compile, and you have to decide what's going to be your loss function. In our case, you're going to be use the binary cross entropy, because you just have a binary classification. Our optimizer, so it's an Adam, means that you're going to be adjusting our learning rate. And the metric that you're going to be checking is the accuracy. So that's the metric that we're going to be monitoring for our data, for our training. So we just compile this. So here is the area that we are going to run the model to train. We are going to provide it for you. If you have GPU, you can run at home, but you're not going to run here. So that's why it's commented. If you want to run by yourself, you just uncomment and you can train your own model. What you're going to be doing, we have the model saved that you trained before, and you're just going to load it in here. So if you want to train by yourself, you have to comment this one actually. So we're going to be loading the history, that's a CSV file, and the model, that is this .models from Keras. So now we have our model loaded. So we're just going to check the summary. So it's the same shape of this one, but we have the models already trained. That's the only difference. So from the history file, that's what we have. It's just the information. That's how was the training during our steps there. So we have the validation loss, validation accuracy. That's from the validation data set, and the loss and accuracy of the training data set, and how was the learning rate of each iteration, because it was changing. Here we are just plotting, just going to run again, but plotting how was the behavior of the loss by each epoch or each iteration, and the behavior of the accuracy. We see that in both cases, mostly the validation loss is decreasing. For the training loss is decreasing. For the validation, it has a trend of decreasing and then a trend of increasing on the end, but it has this kind of trend, but it was a little messy. It's more clear to see in the validation accuracy how it starts to get a better accuracy of our modeling. So what you're going to be doing now is going to be calculating our predictions, and then we're going to resize the images back to 101 to 101. That was the original image that we had for the competition. So we're just predicting for the validation data set, and they're going to compare with the true values of the salt. So it's going to take a couple minutes to run, maybe a little less, because we have the training. Luckily, I'm using my GPU, so it's going to be quite fast. So it's trained, so we create a function now to compare the images, and it's going to be similar as before. We're going to have this image where we have our salt in red, the one that we try to predict. The green one is the true value, and this brownish color is the overlap between them. So it's not the best model that we created, but it's doing a reasonably good job. So if you run this again, we're gonna get another sample of those images, another sample of 64 images that we had before. And we have more examples, so you can keep running these and see. Oh, in a lot of cases, we actually are doing a very good job. We can create a more complex model. Actually, during the competition, we used the ResNet model, not a UNet, simply, and we actually got a better result in this. So for the competition, the score metric was the IOU, the intersection over union. So it's just a measure of the true and the predicted classes or pixels, and see the intersection between them, which one are correct, divided by the union of them, by how much we have classified in the total assault. So this is gonna be perfect if you have one, and the worst possible is 0. So here we are just defining the function for this IOU metric. And one thing that we have to take care is when I was plotting or deciding what is salty or not, was just saying everything that has a probability higher than 50% is gonna be salt. Sometimes we have to choose a better threshold. And that's what you're gonna be doing here. You're gonna be selecting different thresholds and searching for the one that has the best IOU. So you're gonna be looking to here. So our best threshold, I'm gonna say that's gonna be 0.65. So everything that's gonna be higher than 65% is gonna be salt. We need the model to be a little more sure. And I'm just gonna run this and this. So it's gonna take a little while because it's gonna be calculated the IOU for all our predictions in the validation several times, 50 times. So it might take a little bit. And then we're just gonna select what is our best threshold, the one that has the highest IOU. And then we're just gonna plot here what was the best threshold and what was the IOU per threshold, and the predictions, the new predictions that we get with the new threshold for the probabilities. So just waiting here to run. And I'm just gonna talk in advance. Those are the final results that we actually got for the competition. We used a ResNet model. We got an IOU of .837, so it was way higher than the one that's the model that we are providing you. And you can access very similar codes if you go to the TGS, salt identification. You can go to the leaderboard and you can check all the ones that have run in the competition. And some of them provide their notebooks. Sometimes you can learn more about the type of jobs by searching for different kernels. They call kernels, the notebooks here. So here, for example, there is one that provided a kernel. So when you come here, you click, you can see what was this person's solution. So you see how it did the coding and how was his prediction. So he actually trained it several times, the model. He also did some IOU threshold looking, and he also created a mosaic. So he actually tried to rebuild the seismic sessions using all the images that we had. So, and those are his predictions, basically. So this is a very good modeling in the end. For us now, we just finished running. So like I said, our threshold for this model was 0.65, and those are the new results. So we got a slight better result than we had from 0.5. 0.5, we had a shorter IOU. So our best IOU for this training, for this validation data set is 0.684, and that's what we got. So that's it that I had to present for the coding today. I'm going to just go back to the presentation and let's finish with some closing notes. We are in this machine learning block for the learning labs. So we finished it now today, the learning lab 6. We're talking about salt identification. The next one is going to happen in 2 weeks. It's going to be presented by Dr. Brian Russell. And the title is going to be Unsupervised Seismic Phases classification using Python. So it's going to be a very interesting one to watch. So stay tuned, and you're going to be providing more information by the next days. So I'm going to stop sharing, and I'm going to ask if anyone has any question. Please just send a message, and we are here to reply. So any questions so far?
So Marcelo, you mentioned that the original data set had some bad data within it. Is there any way of doing a cluster analysis to clean some of that out of it?
I believe that we could do some way to do some cleaning. I don't know exactly how. It's a little confusing. Something that I noted from those images, that they are not just small batches of the original seismic session. They are also rotated. Sometimes we have the water bottom in the bottom part of the image.
Yeah.
So the easiest way to clean was to reconstruct the image and then clean the classification.
Okay.
Any other question? Okay, let's see. That's okay if you don't have any more questions. So you're going to be stopping the recording, and you're going to be joining. And please don't forget to join for the next session. We're going to have a guest presenter, that's Dr. Brian Russell, and he's going to be using Python, and the same, he's going to provide the coding for us by the end of the session. Thank everybody for joining, and see you all in 2 weeks. Bye-bye.